Okay, so our next speaker is Mohammad Salariseddigh. He is a postdoc researcher in the Residence Communication System Group at Technical University of Darmstadt under the supervision of Professor Wahid Yamili. And he holds a PhD from the Technical University of Munich, supervised also by Christian, and where he focused on the identification problem for molecular communication. So today, he will present on identification over affine Poisson channels, applications to molecular mixture communication systems.
Okay, so hi everyone and welcome to my talk. My name is Mohammad Salariseddigh and the title for my talk is Identification for Affine Poisson Channels Applications to Molecular Mixture Communication Systems. So this is a joint work with Professor Heinz Koppel from Technische Universität Darmstadt, Professor Holger Boche from Technische Universität München, and Professor Wahid Jamali, my supervisor from the Technical University of Darmstadt. My talk is organized into 5 major topics. In the introduction, I would try to introduce some salient and important and famous results in the identification literature. In the main contributions, I would provide the essential contributions that we have done jointly to the field. And then in the definitions, I would briefly review the identification code. And in the main results, I would show you some capacity theorem for the identification for the affine Poisson channels, and then some final results. So in the introduction, I would try to establish the identification problem and its differences to the Shannon problem. So you would see that in the Shannon problem established in 1948, Alice used a deterministic encoder to map the message I to a code word CI, and then the job at the receiver is Bob tries to know, to reconstruct or estimate the original message. So the decoder here declare only one true message, but in the identification problem established in a systematic manner by Salariseddigh in 1989, the job at the decoder is different in the sense that the decoder declares a list of true messages. At least this is the interpretation that was introduced by Verdu, because the difference in the between the Shannon problem and Salariseddigh is that the decoder declares a list of true messages, and then type 1 and type 2 errors might happen. I do not go into the details, but the main job of the decoder is to identify a specific message, J, we call it identifying message or a pre-selected message. So this can be a specific type of cancer or a specific type of color or a specific type of event in the medicine or healthcare. So the applications of the identification problem is in the pessimistic jamming, especially for the deterministic identification, when we assume that the jammer already knows has access to the entire codebook, therefore the using randomization has no virtue, and we can use the identification problem. So in the generalized identification or K identification, also it has applications in medicine, in health monitoring and cancer treatment, in the olfactory molecular communications or odor identification, and in general it can be generalized to any any event-triggered systems when the receiver is not interested in the content of a message or event, but rather to know whether a specific event or a specific message has happened or not. This is the first result established by Shannon for a discrete memoryless channel subject to average power constraint and exponential codebook size. The capacity is proved to be the operational capacity is proved to be the maximum of the mutual information between the input and output, and this is a very famous result in the message transmission literature. And in the identification problem established by Salariseddigh and his colleague, in the double exponential codebook message, at least, I mean, this paper wins a award in the field, and it's one of the most important papers in the field of identification. But again, Salariseddigh and his colleagues proved that the randomized identification problem is the maximum of the mutual information for the DMC, but in a different codebook size, namely double exponential message size. So this is a very strong and different codebook scale, because you can identify more messages, you can identify more DNA tiling, you can identify more coloring, you can identify much more events in networks. So double exponential is rapidly increases more than the exponential. So then in the deterministic identification, in my PhD dissertation, together with Christian Deppe and some other researchers, so we proved that the capacity of the identification with deterministic encoder is maximum of the entropy. So this is stronger than the Shannon results, because in principle, the mutual information is less or equal than the entropy. So in the 6G or in the Internet of Bio-Nanothings, this is a good candidate to be used, because you can achieve more transmission rate. So the scale of the codebook is similar to the scale of the codebook for the message transmission problem established by the Shannon, but the decoding sets here may have overlap, which introduces type 2 error, and it is a new measure, and we have to deal with more complicated methods in order to prove the achievability proofs. So in the olfactory inspired molecular communication systems, this is the system setup that I am dealing in my research currently. So instead of modulation in the time or instant, as was established in the conventional communication problem, we try to encode the message or modulate the message into the type of the molecules. So we have different types, and we do not have delay in the receiver for asymptotic or for very long block length of the messages or code words. So the disadvantage is that the complexity of the decoder increases linearly with the molecule types, but the good news is that we do not have delay constraint, and we can detect in a shorter time the messages sent by the transmitter. So we can assume here that, for example, the triangle inequality has an affinity with the circle with some fractional numbers, and then we would have this affinity matrix which establish the connection between each receptor and the molecule types. And then we want to know what is the capacity of the identification problem over this channel with respect to the features of this affinity matrix, like rank, sparsity, condition number, or other criterion for the affinity matrix. Let's focus on the main contributions that we did. We derived lower and upper bounds on the identification capacity of the discrete affine Poisson channel, subject to both average and peak molecule release rate constraints. We show that the capacity bounds hold for a general class of affinity matrix, and the capacity bounds reflect certain features of the affinity matrix, namely row sparsity and rank. We employ the bounds to determine the optimal or correct size of the codebook, which is a novel phenomenon. It's super exponential. It's not exponential or double exponential. It's super exponential, and it's also different than the previous bounds super exponential, because here T stands for rank, and T might be less or equal than the block length. Let's focus on the code definitions of the identification for a discrete affine Poisson channel. We call 4-tuple and identification codes of n, m, epsilon 1, and epsilon 2, where the codebook size is a function and yet not known. It would be cleared in the proof, but the code words are strings of length n, positive real values, and then decoding sets, and then we would have two average and maximum power constraints. So here the average constraint is different than in the literature for the Gaussian channel studied by Shannon. We do not have this signal or expectation of the signal. That's why we have a linear function. It's not CNI square. And then we have type 1, similar to the error event in the work of Shannon, but type 2 is different, and it explains the probability of receiving a message which is explicitly different than what was sent. So this is a new phenomenon. I mean, here is exactly the point that the rate or the lower bound on the rates are related to the error analysis, and some new and novel ideas would come up compared to the Shannon to the message transmission problem or proofs. So here is the affine model. So we would consider the x to be the model the rate of the molecule released by transmitter over ts seconds, and then we would have this number of observed molecules at the receiver, which is an integer number. It is a Poisson random variable of a sum or a linear combination of the inputs plus some interference, which is a finite value and a strictly more, I mean, it's a strictly positive. But once the lambda is 0, I mean, my achievability works, but for the converse, so far I do not have any result, but we would exclude this case, and then we would have this memoryless transmission problem. So memoryless Poisson law, and then before I present my the capacity theorem, let's focus on the class of the affinity matrix for which the results hold. So the condition 1 is the number of receptors that I showed you in some slides before. K scales sublinearly in the molecule types called K equals n to the power of kappa when kappa is a fractional number. The condition 2 impose a constraint on the number of non-zero entries in each row of A called, so we impose this constraint that the number of non-zero Fk is of order T to the power of L. So namely, we would, so if A is this matrix K by N, so I have K rows, and this Fk, if Fk is the number of non-zero entries in each row, so I would assume that this is maybe m times or m prime times t to the power of L. So this is a constant number, rank to the power of L. So every non-zero entries for each row is bounded by the rank. So we can say that Fk is a big O notation of t to the power of L. And then a constraint on the rank is that the rank itself scales with the number of receptors or the number of molecule types with the exponent, with the condition on the exponent as such. And then we would assume also the singular values of the Gram matrix of the affinity matrix do not scale with the parameter n or k. So, of course, they might scale. And in the literature, if you look at in the mathematical literature, in the linear algebra, you would find a lot of papers that, depending on the norm 1, norm 2, or norm infinity of this matrix, you might have different scales, different bonds, lower bonds or upper bonds on the singular values of a general matrix. And this is exactly the point that it might make it different. The scaling of the codebook would be a function of the singular values. But this is a work under investigation. So in this work, we assume that they do not scale with n, or if they scale, they do not change the scaling of the codebook. So then the identification capacity theorem for a discrete affine Poisson channel with affinity matrix fulfilling the previous conditions subject to the average and peak molecule release rate constraint in the super exponential scale m t of r as 2 to the power of t log t times coding rate is bounded as follows. It is lower bounded by 1/2 minus kappa divided by 4 plus L and upper bounded by this expression. So since they are finite scalars in the, so the optimal codebook scale is determined immediately because we have some finite bounds on it. And then the impact of input constraint before full use of asymptotic approximation is as such, and you would see that the singular values, the minimum singular values might change everything, but for now, let's assume that the singular value is not harmful to the scaling. I mean, if it scales such that this expression is not dominant, then some conditions on the some new conditions on the class of affinity matrix would be established, and this make the results weaker. But I am working on this for future research. So then we have a corollary. I mean, even with this, we would recover the previous results for the Poisson channel that we established together with Christian Depe and Olje Boche. So we exactly recover those bonds, because then the affinity matrix would be an identity matrix, a square identity matrix, and it is full rank. So we exactly recover the lower and upper bonds. Another corollary can be that the identification capacity is infinite in the conventional Shannon scale, exponential scale. So this is again a good news. And then perhaps I can state some ideas for the achievability proof. So we would deal, so the original space for packing spheres or for the achievability proof is that this C0 is the original input space, but then we have an affine. If in general, if we have, so if this is C max, so this is, if this square is the input space for packing spheres, then after applying a general linear transformation, so we would have something like this. So this space, and then for this space, we want to compute the volumes and the number of code words, which is C0A here. And then we have another codebook called reduced affine codebook. We also use Minkowski-Hlavka theorem, which guarantees a saturated packing with density of at least 2 to the power of minus t. But I do not go into the details because of a lack of time, and also the density proof. We also use a lower bound. I mean, the volume of this new space is lower bounded by a function of the eigenvalues as such, and you would see that this is exactly the point that the structure of the affinity matrix might change the lower bound, upper bound, or the scale of the codebook size. So for the decoders, we use a classical distance decoder as such. So the decoder is for a code word CJ when it observes a observations vector y. So we would compute the empirical variance, and then we would subtract the expectation, so to see what is the true messages. I mean, this is a classical distance decoder. You would see it in the literature for the message transmission problem. In the error analysis, I mean, this decoder, even this simple decoder works, and we have results. If you use more complicated decoders with higher statistics, then you might come up with better lower or upper bounds. And for the error analysis, we use the Chebyshev inequality to establish Pavlov decaying upper bounds on the type 1 and type 2 error. And let's focus on the converse proof. So in the converse proof, we consider a sequence of codes where k equals to n to the power of kappa, and then sufficiently large molecule types. The associated affine code book always fulfill this condition, namely the shifted code words. There is a distance between the code words that are packed in the affine space. So this lower bound helps us to arrange a saturated packing, which gives us an upper bound on the achievable rate as such. And then in the asymptotic for the increasing rank and the small b, then it converges to the 1 half plus kappa plus 3L. So the idea is that we use also the continuity of the Poisson law. And yes, this was the main idea for the converse proof. But I mean, the converse proof, still the result that we have, it's not a strong converse. And it's like the work by Alsfede. It's a weak converse because we do not have the constraint that the sum of the errors converges to 1. But this is also a possible future directions for the research. And perhaps this would be a good slide. So, I mean, where we stand, the codebook size for the Shannon transmission problem is exponential 2 to the power of NR. And the codebook size for the randomized identification for the discrete memoryless channel and Poisson is 2 to the power of NR. And the scale for the deterministic identification for affine Poisson channel and also for the wireless communication channel, Gaussian channels, is 2 to the power of n log nr, which is between the exponential and double exponential. We have other extraordinary or non-standard, if you like to call it, non-standard or non-conventional functions like randomized identification for a cover communication for binary input DMC. And also we have, I mean, the best scale is for the identification result and randomization with noise feedback for the Gaussian channels proved by Christian and Holger Buche. So the scale subject to power, to the average power constant and maximum power constant can, in any scale that you consider, capacity is infinite, and this is very strong result. So perhaps I can conclude the talk. What we have done is that we determined bonds on the identification capacity of the affine Poisson channel. We found that optimal codebook size scales super exponentially in the rank of the affinity matrix. And for future directions, we can extend this to broadcast channel, multiple access channel, or MIMO channels. Explicit code construction still is unknown, how we can develop efficient encoding and efficient decoding for specific applications in the 6G wireless communication. We need, I think this is the point that maybe funding can be done, because in the applications you need to deal with the finite Bloch length. And then finite code word length, studying non-asymptotic identification capacity, how for a finite bond, how far we are from the asymptotic bonds. And for more general class of random affinity matrix, like when I mean, we assume that the entries of this matrix are deterministic, but once they are random, then what would be the result? What would be the lower bound, upper bound? So in the literature, it is known that for random, if you generate Bernoulli or Gaussian random entries, then the rank is at most with probability 1 is the matrix is full rank, and this can be also a good topic for the future directions. What would be the bonds on the identification capacity for a random matrix A? Yes, and this is what I have done. And if you have time, questions.
Yes, thank you for the nice talk. Are there any questions or comments?
Okay, so I have actually a couple of questions.
Yes.
The first one is about the converse proof.
Yes.
You showed that you can achieve the 3/2 result that from your previous paper on Poisson channels.
Yes.
We recently proved together with Christine and some others, and in a very easy manner, that you can actually get 1/2
Okay. Yes.
instead of the 3/2. Is there any way to apply these results on your proof, or your converse is far away? I mean, maybe because of the power constraints, it cannot be applied our method, but Have you looked at that?
This can be a possible solution, but I mean the method is more or less similar to the works for the standard memorious Poisson channel. But yes, if you apply those ideas that you get the 1/2 upper bound, I mean it's improved by from 3/2 to 1/2. Then maybe we have yes, this can be. I didn't apply those results. Maybe this can be an improvement in my research or collaboration or
Sure. And the other question was an actual question about the chipability part. You show that this when you showed the capacity bounds that it was 1/2 or some sum of terms.
this
Is there any way? So I can see that I can be 0. Is there any way that kappa can also be 0 in single settings such that the lower bound is 1/2?
So this kappa in general can be between 0 and 1, right? Because we assume that the number of receptors is I mean, k is n to the power of kappa when kappa is between 0 and 1. But in the analysis, we have a condition that I bring it here, a kappa plus L inverse less or equal than tau. So this condition induces that kappa to be between 3/4 and 1. And L should be between 1/4 and 0. So still, we do not have the results for kappa between 0 and 3/4 because the methods that I developed in the error analysis, right? Maybe one we come up with more advanced in the error techniques in the advanced, and then yes, this is a possible again.
Cool. Thank you.
Yes.
There was really a lot overlap with the question. But,
Yes.
I have another question. Yeah, we have this joint paper with ISI when we consider the Poisson channel with ISI.
Okay.
Is it included here? Can you see it as a special case here in this setting here? I think yes, or?
Yes, the lower bound is exactly recovered. I mean, because this is a general.
Yes,
Affine Poisson.
exactly. It's
It
more
must be
general.
also applied to when we have a Toeplitz matrix structure. It is the ISI Poisson channel.
Yeah.
The lower bound exactly match. The upper bound, it's not optimal. I'm working on it for the journal version or for the improvement. Yes.
Yeah. And
But-
also for the lower bound, you know that we have this for the Gaussian channel, we have this galaxy code construction
Yes.
where we improve the lower bound, and we are also working on the Poisson channel at the moment to see,
Yes.
and we think perhaps we can apply it there, and it should be also perhaps it's more difficult now to
This is-
generalize it more, but if you just look at the DTPC, then it should work. So perhaps
Yes.
it's my guess.
This is also a good idea to apply those galaxy coding and this improved bond to this and to improve this perhaps by a factor of 1/2 or something between 1/2 and 3/8. I think you improve it.
3/8.
Yes, 3/8. Yes, this is improved. This is another idea. Yes.
Mhm.
But I am studying those papers and those posters or papers to see whether yes,
Yeah.
this is also a good idea.
Okay. Yeah, interesting generalization. Thank you.
I mean, this is also available on the archive if one wants to come up with the exact methods and proofs. This is available on the archive.
So thank you for the nice talk. And we will